Hello, welcome to the UW Undergrad Research Symposium. My name is Han Hiller. I'm a member of Arthur Bernard's Quantum and Classical Nanosystems Lab. Today I'll be discussing electron hydrodynamics. My goal for this talk is to first explain the difference between ohmic and hydrodynamic conduction, and then I'll be talking about the material we're experimenting on, graphene, and after this background is out of the way, I'll be able to discuss my project and share some simulation results, discuss the experimental setup we'll be utilizing, and our next steps. Most electricity that we encounter in our day-to-day lives is ohmic. For example, the electrons in the jumper cable to restart your car are in the ohmic regime. Qualitatively, we describe ohmic transport as electrons being strongly coupled to lattice sites and weakly coupled to each other. So the collisions that dominate the transport are ones with ion cores, tending to reduce the net electron momentum. Quantitatively, ohmic transport is described by Ohm's law. The current density is in the direction of the electric field and inversely proportional to a material property called the resistivity. Equivalently, voltage equals current times resistance. However, in the hydrodynamic limit, electrons are strongly coupled to each other and weakly coupled to lattice sites. So the collisions that dominate this transport are the electron-electron collisions, where many occur before the momentum-relaxing collisions with ion cores or edges. What's interesting about the hydrodynamic limit is the electrons behave as a viscous fluid, sort of like honey, and it's this viscosity that gives opposition to flow rather than the resistivity of the material the electrons are flowing in. However, it's hard to find systems that support the hydrodynamic limit. Enter graphene. So what is graphene? Well, it's a 2D material, meaning it's a 1 atom thick lattice of carbon atoms, and it has many interesting properties. It bends like rubber, but is stronger than steel. It's extremely clean and conductive because it lacks lattice defects. As a result, it is a very efficient conductor of electricity, and importantly for us, the hydrodynamic limit is observed at a range of temperatures between 40 and 60 Kelvin. Now that we've gotten this background out of the way, I will discuss some of my work. So I started this project by modifying and running simulations. The basic idea is that electrons are injected through the center of these dome devices and are absorbed along the perimeter. In between this injection and absorption, the electrons behave like billiard balls, scattering off one another in momentum-conserving collisions. In the results at right, we see the crossover to the hydrodynamic limit. In the left plot at 4 Kelvin, nearly all the electrons injected from the center end up on edges nearest the center of the dome, whereas at 60 Kelvin, there's appreciably less electrons at the center and more towards the bottom of the device, suggesting whirlpools are causing electrons to migrate away from the center. For the measurements we'll be performing, I built these feedback lock-in amplifiers. We need amplification because the nanoscale devices output microvolts, whereas computers read on the order of 10 volts. So these circuits amplify with a variable gain, mitigate noise, read out a voltage, and source a current via a feedback loop. We have 32 amplifiers that we can position in parallel along a device, which allows us to accurately characterize the flow profile in the same way we do in the simulations. Here's a high-level schematic of our experimental setup. We place our devices in a chip carrier, which then goes inside a cryostat, basically a refrigerator powered by liquid helium that can cool to 4 Kelvin. Then electric leads are placed along the device, which, mediated by my amplifiers, are attached to a computer, and using home-built Python code, we can take electronic measurements. Ultimately, we'll get a very accurate sense of the electron transport in this device at a variety of temperatures. So next, we're looking to fabricate these devices, place them in our cryostat, and conduct measurements on them at a variety of temperatures and probe tip locations, with the end goal of comparing these experimental results to simulation results and deducing properties of electron flow, such as the viscosity and boundary conditions. Alright, that's all I have for today. I'd like to give a special thanks to my PI, Arthur Bernard, the Mary Gates Endowment for Students, and all you for listening. If you have any questions, I'm happy to answer them now.